All right, this is part 2 of rivers. We've talked about the drainage basin already. We've talked about the channel and the various things that we can measure in both of those. We've talked about how sediments can erode and transport their sediment, and how velocity is a very important component of what a river is able to transport. The other thing you'll notice on this slide that we left off with on the last time is that we also have slope listed. Now, slope is not part of this graph, but it turns out that the slope of the channel is an important characteristic when we want to know how much energy a river has to transport its sediment. For example, the bed load can be improved if you can have a steeper slope, because it's easier to push things down a steep slope. So gravity is part of the equation as well if we bring slope in. So what kind of changes do we see as we move from the headwaters, which are labeled H on here, downstream to the mouth of the river, which are labeled D and M? So one of the things you'll notice that you would expect is in the channel characteristics, the channel gets wider as you move downstream. The velocity gets higher. Now, this is not necessarily what a lot of people think, but you'll notice on this graph that as you move downstream, the water velocity increases. It turns out that although the Illinois and the Mississippi River look like they're kind of lazy rivers, if you measure the velocity of water flow, they're actually quite fast. They don't appear that way because the banks are smooth, and so everything kind of smoothly moves downstream. And that's actually one of the reasons why the velocity is able to increase as we go downstream. And if you go back to the previous slide thing, we mentioned the channel roughness. When they were initially developing the equation for flow and related it to other stream characteristics, they had things that you would expect, like width and depth and the slope of the channel, but it didn't match up with the data that they had. So that's where the researchers said, you know what, there's something else going on here, and that's when they identified roughness as an important characteristic. The other thing you'll notice is that as you move downstream, the sediment transport size, if you look in the lower left-hand corner, gets smaller. This is not surprising, and we'll be looking at some pictures in a little bit. Usually in mountain streams, you see some pretty large materials, and when you look in a stream like, or a river like the Illinois or the Mississippi, you don't see large stuff at all. Now, why would that be? If the velocity is higher, we should be able to move larger things, and it turns out that we can. If you drop a boulder into the Mississippi River, it will push it downstream. The problem is, as it goes downstream, it's bumping into other things, it's wearing down, and remember, the sediment size, or actually I shouldn't say remember, one of the things that you might observe is that as you move sediment, it gets weathered and it gets smaller. So the reason why the sediments are so much smaller as you move downstream is it's the result of weathering. So the particles tend to get smaller and rounder. It's not that the river couldn't move them. It's just that they're not available. You will notice, however, that the total stream load of sediment goes way up along with the discharge. So as our volume increases, so does our ability to carry sediments and move them downstream. So let's take a look at a few examples of some rivers. We're going to look at 3 different channel types. The one on the left is called braided. The one in the middle is often referred to as straight, although you'll notice it curves around a little bit. And then the one on the right is called meandering. The straight channels are typically something that we find in mountains. You'll notice that because of what the river is doing here in the mountainous area, it tends to be cutting down into its bottom. And this is called stream incision or vertical erosion. We'll be looking at this in lab this week. But that tends to keep the stream channel fairly straight because it's cutting down, the sides are caving in, and it's very busy moving that large material, and it tends not to erode much side to side. It tends to maintain a straight channel. You'll also notice that the sediment pieces here are pretty big. We've got some pretty large boulders, and you might think that little river can't move those big boulders. And that would be correct in its current state. But if you get a large rainstorm, this channel is going to fill up with water, and the water is going to go fairly quickly. But the other thing it's got as an advantage is it is pushing those boulders down a fairly steep gradient or steep slope, which helps it move things. And of course, as the boulders roll along the bottom, they're going to get beat up and get smaller. So that is what we see in the mountains. If we go out in front of the mountains, we had all that sediment, and we have a fairly straight and confined channel. When we get in front of the mountains, and I should say a fairly steep gradient, so we can move some pretty big pieces. Once we get in front of the mountains, however, conditions change. The slope changes. So our ability to move large pieces of sediment decreases. In addition, the channel can spread out, and in this case you'll notice it's a little wider, and because the water is not confined to that single channel, that also decreases its ability to move large pieces and lots of material. And so what we see is what's called a braided channel. This is a channel that is basically choked with sediment. Again, when the water rises up, so if you get a big rainstorm, it can move most of this sediment. When the rain goes away and you're at what we call base flow, which is kind of the minimum amount the river usually has, it has to find its way through the sediment. So these are our braided channels, lots of sediment, and during many times of the year, not the ability to move that sediment is decreased, and so you end up with this braided system. Our next channel is something we're going to spend a little bit more time on, and that is what we call a meandering river. You'll notice that this river has a fairly wide valley. It's the area from here all the way over to here, and then it's got a single channel. In some places it's got like a split channel, but for the most part it's got one main channel that kind of wanders around. And what's happening here is that you have a relatively low gradient, so a low slope, and the river is able to use its energy moving side to side. It actually is going to be eroding its banks quite a bit. And so let's take a look at what happens if we look at the profile of a meandering channel. And it actually ends up telling us a lot about how rivers work. So remember how we said in the previous slide set that the fastest water tends to be in the middle of the channel just below the surface. If a river has a little bit of a curve, the fast water is going to end up on the outside of a curve. Just like if you're driving your car, when you hit a curve, you end up at the outside of the curve. This means we have more energy on the outside of the bend, and that extra energy can be used for erosion. On the inside of the bend, however, it's just the opposite. Things slow down, and as we lose energy, we tend to drop sediment off. So the inside of a bend collects what we call a point bar, which is a deposit of sediment, while the outside becomes what we call a cut bank, where we have active erosion. The end result of this is that once that water starts moving in even a little bit of a curve, the erosion on the outside of the curve and the deposition on the inside of the curve is going to cause that curve to get bigger. And over time, you can see that curve gets bigger and bigger. We would call it a meander because it's winding around so much. And you'll notice on this drawing, the two cut banks here and here reach each other, cut off the bigger bend or the bigger meander, and the process starts over again. So this is what we call an oxbow lake, or a cutoff meander. And over time, it will fill in with sediment, and we will look at a couple meandering rivers in the lab exercise. So here's a picture of a meandering river from a satellite image. You can see Oxbow Lake. You can see cutoffs here and a lot of wandering around. So that's our example of a meandering river. If we look at our river, the Illinois River right here behind the college, you'll notice that we do have a big meander right there as well. And we'll take a look at that toward the end of these slides. So I'll have to kind of speed up a little bit. Next to the river, we very often get deposits of sediment. And one of the processes that we look at is the formation of what we would call a natural levee. Here's a river and its banks. You'll notice there's a hill on either side of the river. Seems a little weird, but if you think about what happens when the river floods, it floods the flat area next to the river that we call a floodplain. And as the water leaves the main channel, it gets into this shallow floodplain with vegetation, and the water slows down. When the water loses energy, it deposits sediment. That energy transition is right here at the banks of the main channel, and so it deposits the sediment, a lot of sediment right there, and creates what we call a natural levee. If we go back to this picture of the Illinois Valley, you'll notice right next to the Illinois River there, we have some high ground. This part's flooded, this part isn't. This is a natural levee. As the water leaves the Illinois River, it hits those trees, it slows down, it drops sediment, and creates the natural levee. So you'll notice that we get a deposit whenever the river loses energy. Here's another example. Well, again, we'll take a look at one of these in the lab exercise. River's got a lot of energy up here in the mountains. It's fairly steep. When it hits this flat surface in front, it loses its ability to carry all that sediment, and it dumps it out into this feature that we call an alluvial fan. And here's a set of alluvial fans that you might see in along the edge of Death Valley. They're kind of running into each other. Very often we look at alluvial fans in desert regions because they're so easy to see. I'll give you a local example in a couple of minutes, right before the slide thing is over. The other place the river loses energy is when we get to the end of the river, where it empties into a body of water. In this case, the Mississippi River empties into the Gulf of Mexico. It loses its energy and dumps its sediment. So this is the active part of the Mississippi River Delta. So a delta is kind of like an alluvial fan in the water. And you can see it's just piling up the sediment year after year. The one thing that makes the Mississippi Delta a little unusual is that humans have altered the flow of the river, and so the delta sticks out a lot farther than it otherwise would. Normally it would switch and make a new channel over here. It would keep switching back and forth and kind of widen that out. So this is kind of how deltas work. You can see that we've got a little sloping edge on the front where it's dumping off sediment. The Mississippi Delta actually has been filling in the Gulf of Mexico for millions of years, and this kind of shows you that tip of the delta at the north is actually southern Illinois. It's been filling this in with sediment literally for tens of millions of years. This is a side view. As it keeps piling that sediment in, the crust underneath it sinks down, and we get a thicker deposit. And I think what I'm going to do is I'm going to end the slide presentation now. There will be a very short third slideshow which will show you where we can find some of these features in the Illinois Valley.